Okay, so here we have an alkene, and we have H2, and then the palladium. So for this one, don't forget your rules. All right. So what are the basic rules we talked about doing? We talked about numbering our carbons. All right. We should number our carbons. So 1, 2, 3, 4, 5. We see H2 and we see palladium. We should, right, all these reactions we've been doing are addition reactions, right? So we're adding stuff across pi bonds, right? In this case, we're going to add H2 across a pi bond. So you should also recognize that this is one of the reactions you don't need to know the mechanism for, but you need to know something about the stereochemistry about it, right? So a lot of things you need to be asking yourself for all these problems is this reaction a regioselective reaction? Is it a stereoselective reaction? Do I need to know the mechanism for it? Right? So in this case, no, you don't need to know the mechanism, right? You don't need to know the mechanism for this. Do you need to know something about regioselectivity for this? No, why not? So regioselectivity is all about picking one region of the alkene, right? Saying, I'm going to put something on 2 instead of putting something on 3. That's what regioselectivity is all about. In this case, it doesn't matter because we're adding what? We're adding two things, but they're the same thing, right? We've been adding 2 things over and over again, but they've always been 2 different things, right? But here we're adding H's to both of these carbons, so there's no regioselectivity anymore, right? So we're adding H to both, right? So it's the same thing. So it's not about regioselectivity. Is there something about stereospecificity or stereoselectivity? Yes, there is. So this, right, remember we talked about a little bit about the metal being like a surface and the alkene kind of coming down on it, right? And the alkene's going to come both from the top, right? The alkene's going to get the H's from the top and from the bottom, right? So the H's are going to add from the top, or they could also add from the bottom. And there's no preference, right? Because, right, in this alkene, there's what? There's a pi bond, right? Remember what a pi bond looks like? Does the shading, does that tell you where the electrons are at? No. No. So the electrons are just as much on the top part of the pi bond as they are on the bottom part of the pi bond. So the H's are going to add to the top part of the pi bond just like they're going to add to the bottom part of the pi bond. Right? And they're going to add together at the same time in a syn or cis fashion. Right? The H's are both going to add both to the top or both to the bottom. So how do we think about that or look at that then? So I'm going to shrink my pi bond down. The way I like to do it, I redraw this and say, okay, wait a second. Right? Carbon 1 and carbon 4, they're both on the same side of that pi bond, aren't they? So I'm going to make those both be wedges. Because if they start out on the same side of that pi bond, they're going to stay on the same side of that pi bond, even when I add the H's. Carbon 1 and 4. These 2 hydrogens are both on the same side. Right? These 2 hydrogens are both on the same side. I'm going to draw them both hatched because they're both on the same side. Now when I add H, I can either add H again, I can either add to the top or I could add to the bottom. So I need to draw both cases. So here they are added to the top. Notice they're both on the same side, they're in the same plane. That's a syn addition. Is this the only product I'd make? No, let's back up, make sure I number my carbons, but is this the only product I'd make? No. How do I draw the other product? Keep the wedges and the hatches the same and just put the H's on the other side. So the other product, right, nothing changes. One, 2, 3, 4, 5. Now instead of being on the top, the H's are going to be on the bottom. Now another tough part about this, another layer that they could add to this, which is not the case here, is so when you add something, is it potentially, if you turn something from an sp2 hybridized carbon, carbon 2, into sp3, potentially that could become what? A chiral asymmetric center, right? Potentially that could happen. Is that the case here? Did these become asymmetric centers? Did either of them become asymmetric centers? No, why not? Because both of them they don't have 4 different things bound to them. Now, some of the tougher problems in sapling, right, will take this exact thing, right? Do you understand the stereoselectivity, stereospecificity? But then on top of that, when you add these H's, you're creating a chiral center, and you need to decide, is that R or S? That's the second level, right? That's, okay, here's the reaction, right? You need to know how that works, the syn addition. And then the second level will be, okay, let's go back and remember, did I make a chiral center? Now I got to figure out, is that R or S? And what did I make? Did I make enantiomers? Did I make diastereomers? Right? Usually you make enantiomers, right? You make, right? Because if you add from the top, that's like adding R, or if you add from the bottom, that's like adding S. You'd make diastereomers if there's another stereocenter somewhere else in the molecule that never changes, right? So that's that second level with this, right? So you need to know the stereospecificity with this, but then you got to be ready to realize, oh wait, did I make an asymmetric chiral center? And if I did, is it R or S, right? Did I make one or two? And then what did I make? Most likely time you made enantiomers, right? Two mirror images. All right, so let's take a look at halogenation. So halogenations, of course, involve Cl2 or Br2. I'm just choosing Cl2 here. So again, as we've talked about, right, every step of the way we need to identify our nucleophile and our electrophile. We also should number our carbons. So if you're short on time, at least number the carbons near the pi bond. Also, we talked about drawing in the H's on the alkene too, right? So let's draw in the H there. Make sure we have all our lone pairs. I already took care of the lone pairs there for you. So what's my nucleophile? I don't have the products, so I can't do bonds broken, bonds formed. What's my nucleophile and what's my electrophile? Nucleophile is the pi bond. So this is weird. People are like, well, chlorine can't be an electrophile. But remember, think about, right, one end of this CCl bond, right, one end could be more delta plus, like the electrons can kind of slosh back and forth, right? Right, the evil twin versus the positive twin, as I told the 9 o'clock class, I think, right? If I had an evil twin that was super negative, was over here, but I'm super positive, so I'm over here, right? So we have a polarized bond, even though we're the same. Okay, so our nucleophile is the pi bond, and we talked about the polarizability of that CCl bond, the Cl-Cl bond. So show our pi bond. That's going to attack the chlorine. At the same time as that happens, this chlorine-chlorine bond is going to break, and those two electrons are going to that chlorine, the negative chlorine. And now this other one is going to come back, looping around, and we're going to put it there. It doesn't matter if you put it to carbon 2 or 3. It doesn't matter, right? As long as you're showing it go to one of those carbons, it doesn't matter which one. Make sure you show there's electrons coming back from the chlorine or bromine attacking a carbon. Doesn't matter which one you choose, right? 2 or 3. Okay, so that happened. Now what? Well, now I redraw this, right, with the knowledge that this carbon 2 and carbon 3 are trigonal planar geometry. They're flat. The chlorine could add from the top or the bottom, so now I need to add some wedges and hatches. All right. There's an H. Notice, hopefully, this H and carbon 5 are on the same side of the pi bond, right? You'd say they're on the same side, cis. So they better be both wedged, right? These two carbons back here, 1 and 4, are also on the same side, so they have to be both hatched. Right? So 1, 2, 3, 4, 5, 6. And I might as well just draw this twice right off the bat, before I even draw anything else. I might as well just redraw this twice. I'm going to have to redraw it twice because I know full well that the chloronium ion in this case can add both from the top and the bottom. 1, 2, 3, 4, 5, 6. So first one I'll show the chloronium, Cl plus, there, and I'll show it a little easier to see it maybe down here. Still has its lone pairs, still has 2 lone pairs. Now imagine you have, right, so when you do that, you're going to also make a Cl minus in both cases, correct? No, why did I have to make a Cl minus? To balance that charge. That's rule number 4 of the mechanisms. Balance thy charges. Balance thy charges. Now, if there was nothing else, one of the things I just talked about in the reaction overview, we had to worry about solvent, right? You always kind of got to be thinking about solvent. Is there solvent around, right? Because now I'm here and I say, what's my electrophile? What's my nucleophile? So as I look at this, which of these carbons, carbon 2 or carbon 3, in both cases, which one do you think is more likely to get attacked or is more delta plus? 2 or 3? 3. Why? More substituted, so it's more likely to stabilize that positive charge, right? It's more likely to handle that delta plus, right? It's not, is there a carbocation here? So be careful, right? I said delta plus, not full-on plus, delta plus. So that carbon's the one that's going to get attacked for sure. That's the regioselectivity of these. The question is, who's going to do the attacking? Is it going to be Cl minus, or is it going to be the solvent? And up here, I showed 2 possibilities. Right? I said, let's go through each one. So the one you've seen, this is ethanol, an alcohol. So a solvent with lone pairs, but also whatever has lone pairs is also bonded to hydrogen. It's also bonded to hydrogen. Notice CHCl3, the thing with lone pairs is what? The Cl. So if I drew that, right? The Cls have lone pairs, but let's take a step back and think for a second. Does chlorine like to have, how many bonds does chlorine like to have? 1, right? And where's chlorine at in the periodic table? Farthest to the right, and what do you know as you go farther to the right, what happens? Electronegativity. Do you think chlorine is really gonna, chlorine has lots of electrons, lots of lone pairs, sure, right? Just drawing them in. Do you think chlorine's going to be willing to donate those lone pairs? Well, no. No. Now, somebody can say, well, what about oxygen? Oxygen. You're right. Oxygen's not super happy about it, but it can be relieved by having this H fall off and remaking H+. Whereas the chlorine, right, because it doesn't have a hydrogen there, right, because it can't, right? There's no way to fix that problem. There's no way to fix, if these lone pairs attack carbon 3, you're stuck with a chlorine with a plus charge, and there's no way to fix it. Right? There's no hydrogen to fall off and make H+. Now, if this oxygen attacks, right, we know for sure it's attacking carbon 3, and we know for sure it's attacking cis or trans. Trans, because right, where's sigma star, right? I'm going to draw sigma star here. That's where the electrons are not at. So we know it's going to attack trans. Whatever attacks is going to attack trans, and it's attacking carbon 3. But the alcohol, when this lone pair attacks, it makes a plus charge on oxygen. Not great. Still has a full octet. But you can have that hydrogen fall off and make H+, which is much better. So let's take a look at that. So that attacks there. As you put electrons in sigma star, what happens to the associated sigma bond? It breaks, and that would be, now be careful, some people are going to want to break carbon 2 to 3. No, you want to break the bond between carbon 3 and chlorine. Don't break the bond between carbon 2 and chlorine. Look where your electrons are going. They're going towards carbon 3. So that means carbon 3 needs to lose a bond. If it makes a new bond, it must lose a new bond, lose an old bond. So those 2 electrons will go to the chlorine. So I'm just going to show one possibility for the mechanism here, because of course this would also, there's a lot of solvent around, right? Solvent implies there's a lot more of that than Cl minus. Even though is Cl minus a better nucleophile than the solvent? Well, sure, it has a minus charge. But, right, if there's a billion of these and two of these, right, the numbers went out, right? So it's not just about reactivity, right? We talked about rates, we talked about concentration as well, playing a huge role. So it attacks. Carbon 3 to chlorine bond breaks. The chlorine is now there, right? There's that H. Notice my wedges and hatches never have to change. If I do it this way, my wedges and hatches never have to change. Lot less chances to screw it up. Where's that ethanol at? It would be here on carbon, so do our carbon, 1, 2, 3, 4, 5, 6. The ethanol will be up here. One common mistake people make is they'll forget, right? Did this OH bond break? No, it did not. Did this carbon-oxygen bond break? No. What is the nucleophile in this step? The nucleophile is the lone pairs on the oxygen. No bonds to oxygen are breaking at all, right? The lone pairs on the oxygen are the nucleophile. So this hydrogen is, of course, still there. Move that out of the way. And there's still one lone pair left. Now be careful, of course, we need to ask ourselves the final question we always ask ourselves before we're done with the mechanism is what? What's our last, what do we need to ask ourselves here?
Charge.
Did I balance my charges? What was the overall charge over here? 0. So what am I missing, right? So I do an arrow. What am I missing over here? I'm missing a couple things. Plus charge on the oxygen, right? Notice how the oxygen has, how many bonds does the oxygen have? It has 1, 2, 3. How many bonds does oxygen want to have? 2, right? What else am I missing? The Cl minus is just along for the ride, right? To balance my charge. Now the last step is what? This H just simply falls off as H plus. Now sometimes you'll see the Cl minus take it, and some people could say, well, what, you just told me about concentration. There's no way the Cl minus is going to find that. And you're right, that's okay. Because H plus is the same as HCl. HCl is what? A reactive strong acid. You can just, HCl is just H plus. Just like H2SO4 is just H plus, right? So if there's no if there's solvent involved, this becomes a role. This matters. So the final product would be, so then the final product is a alcohol or an ether? It's an ether, thank you. And to make sure we balance our charges, I'm just gonna shrink that down. We're not worried about that anymore because that was the example. The oxygen is there, right? Number our carbons, 1, 2, 3, 4, 5, 6. We also have the Cl that's right there. Notice the relationship, the chlorine and the alcohol, the ether here, this 2 carbon piece, they're trans to each other, right? I need to balance my charge. What else is there? I made H plus, right? I made H plus in this final arrow, right? When I did this final mechanism arrow. And I also had always along for the ride was Cl minus, right? How many steps is this reaction? How many transition states are there? There's 1. So this first one, right, where the chlorine minus formed, that's 1, right? So think how many times you use mechanism arrows. You use them once, you use them twice, and then use them 3. So there's 1, 2, 3 arrows, reaction arrows. That means there's 3 transition states, right? Because mechanism arrows show the breaking and making of bonds. That's what transition states are. How many intermediates are there? 2, right? I mean, these are the same. These are enantiomers of each other, right? Mirror images, but they're essentially the same intermediate because enantiomers have, of course, the same physical properties. Then you have this other intermediate, and then the final product. What intermediate do you think is higher in energy? Intermediates A, the chloronium ion, or B? A, why? Everybody has full octets. Ring, I would say, I think 2 things. I would say, who has a plus charge? Chlorine or oxygen? Who do you think matter about that? Maybe, I mean, that's kind of, they're that diagonal, it's hard to know. So maybe that's tough to say. But the other thing you can think about, ring strain, right? The chloronium are in like triangle. What's the bond angle of triangles? 60 if it's equilateral. No, it's not equilateral. So it's strained, right? It's for sure not happy, right? Because these are sp3. These are sp3 hybridized carbons. What's the bond angle for sp3? 109.5. So these are not happy. So this is probably the higher energy intermediate, right? So if you're thinking about your free energy diagram, these should be higher than this intermediate, right? And the energy to get to this one would probably be higher. The highest, the slow step would be making this because it's just a high energy intermediate. So a good question is, what am I asking? What do I ask for products, right? So if I say show all products, I want this, and then the enantiomer of it, where the chlorine here is up, and the ether part is down. That'd be both, or you could say plus enantiomer, right? If I ask for both, I want both.
But if you say draw,
Give me one product. And show stereochem, right? Make sure, if you should always be thinking, do I need to show stereochemistry? You probably should, right? So yes, there'd be two products here, two enantiomers you made, essentially. What? Nope. The major organic product. That's like Sapling's been asking for, the major organic product, right? Because organic means carbon. So this is the major organic product. This is a byproduct.